Alright, so in the previous lab we did power system parameters. So in this one we'll be continuing onto power flow analysis. So based on the data sheet, we're supposed to modify the network, right? So the network should be looking like this right here. Also, there's new data to work from. In this one, we will be using the part factor right here. Yeah, so okay. Check if this is recording. So create the system shown in figure 1. This is a modification of a network used in laboratory. Alright. Okay, I see. So you see the specs of this 13.8 volts. So what I'll be doing right now, I'll be removing this generator right here. I'll be creating a new bus bar. Yep. My bad. Yeah, right here. 3 miles gen. This one should be 13.8. Let me confirm. Yeah, 13.8. So right here, generator right here, but we have to invert it. It's not right there. So be using a transformer. So we'll be using the same specifications from the previous lab as what we used for this transformer right here. Right. So this one should be connect. Alright, so connect it to the 3 miles bus via a transformer from the 3 miles generator bus bar. So the transformer should be run from the 3 miles gen bus bar to the 3 miles bus bar. So for the specs, let's see, we'll be using the previous specs. 0.14818. Well, let me just leave that because I will have to change the MVA. So adjust the transformer ratings of the two transformers at 3 miles gen and Huntsby to 50. 3 miles gen and Huntsby. So Huntsby 3 miles gen. 50 MVA 50 MVA. If you notice, there's an overload. So that's why we'll have to make some changes to the generator. So change the era megawatt control from none to partition factor control. So choose a random area right there, right there. Partition factor control. Right. Save. That's it. Um, Now update the generator information as indicated in table 1. So V6 we will be using the information from right here, so we're dealing with V6 right now. So W max 65.1, W min 0, var max 42, var min 0, partition factor of 5, enforce. Also, we would have to fix the set point, put it at 48 and 10 mvar. So that should be good. Second generator. For the Huntsby gen, that would be MW max would be 32, correct? MW min would be 15. These, yes. Min mvar 0. Partition factor of 2.5. And as for the set points are really important. If it's not correctly done, when you run the circuit, you will basically have to redo a bunch of stuff. I mean, that's based on my experience, really. Then for the 3 miles gen, again, same data sheet. Min MW 10, max MW 22, yep. Min mvar 0, 21. Partition factor of 2. Set points of, what's this, 19, 13. Cool. As it relates to this, need the field. Yeah. Alright, so the Generators have been updated. Just double checking have been updated based on the sheet. Yep. So having modified the network, run the load flow ensuring that the output shown in figure 2, so that the output is shown as in figure 2. Hint, allow the program to automatically allocate determine generation output. Um, oh, based on the diagram in figure 2, they have the system load, so I'm gonna show you how to do that because I know I did not show you in the parameters lab. So um, field area, so system load, area again, import load. Alright, so these would be the yeah, you know. So alright, let's run that. So by running this we realize hey, everything is almost perfect, you know. This is slightly off, but you know, yeah, it's fine. Based on the diagram shown in the lab, they were using they were basically just using the decimal like a whole number. They were just using a whole number, so like 13, but I'm using 4 dp, so a 13 for me is like 12.7251, you know, but it's fine. um so I'll be going through just a few stuff because this lab isn't that difficult. Basically, as I previously mentioned, is a lab 2 will be focused on the injection of reactive and active power. Basically, its effects on the bus angle, or you can say the load angle, or um the voltage. Yeah. So um using the loads at each of the load buses vary the active power 50% above and below the nominal values given in 10% increments while maintaining the nominal reactive power. So basically what you will be playing with would be these so these are the values that you'll be like varying, you know. And each time you vary them, like you record the per unit voltage and the load angle. By load angle, I do not mean the phase angle. I mean the voltage and I mean the bus bar angle, you know. That was a major issue as stated by Dr. Isaacs, you know. So just for the orals, you know, it's good to know. So part 4 spoke about what? Restore the system to its original load values owing to increasing whatever. Oh yeah. So basically for this one, if you remember the formula that says the power factor is equal to the active power over the square root of p squared plus q squared. Basically, that's p over s, which is the apparent power. So basically, you're gonna find a way to like inject q reactive power without without changing the active power, really. So by using this formula, transpose, do all those fancy stuff, um you'll have to maintain the new active power, you know, as I stated. So as the Excel sheet would show you, the power factor currently is like 1 or 0.999, and I'm going all the way to 0.7. So, you know, by making the active power constant, I'm still finding a way to reduce the power factor. So, yes, by the injection of reactive, and then I would like record the losses, active losses, the reactive losses, the bus voltage. The load angle right here is incorrect. These were supposed to be the, as I said, the bus voltage, not the phase angle, you know. So yeah. Um, by drawing on the knowledge gained from lab 1, implement a solution restoring the original bus voltage while serving the new load demand. So um, there is a quite easy way. Um, oh yes, everyone did the mid semester and did the lab already. So you would have noticed that a shunt capacitor can be used as basically like as a reactive bank. So you can restore the voltage by adding a shunt capacitor um, from, I believe it's, is it this? Hold up. Yeah, I believe it's this. Yeah. So um, you would basically choose a value. You would basically play with this value until the voltage is restored, really, you know. Oh yeah, here it says mvar. um well, there's another way that we could have done this. We could have done this by means of load shedding. Load shedding is whereas you remove the loads from the network that does not require power at the moment, but seeing that we need to um keep our current keep our current circuit, we don't need to trouble like any of the components like that. So um how were the voltages at voltage control buses impacted by the load change? Well, you guys are smart. I'll just move on. So 7 is speaking about the Y bus matrix that can be found in the model explorer. So there's a long way and there's a short way. I'll just show you the short. Well, alright, I'll show you the long way. Um, this solution Y bus. Well, hold up. Yeah, make sure it's on run. So this is what you will like extract to Excel. Um, yeah, send to Excel. And there's a short way. Instead of doing all that, you could just go right here. Um, Y bus. Yeah. Um. Oh yeah. So the Y bus thing. Let's say you have a bus bar, right? Basically, with the Y bus, you will like add up like all the impedances that are connected to that bus bar, like to get the total. If you remember from networks 2, basically, so let's call this what, y11. This would be the total because only one line is connected to this, or diagonally you can see the total. So right here would be the sum of this and this, you get what I mean. And that's basically it. The lab is, um I may do I may do lab 3. You guys can let me know in the comment though. So have a good night everyone, and all the best on the orals tomorrow and Thursday. Thank you.